So let's get into subject then. Today we're going to talk about factors that cause clogging of irrigation systems. We're going to talk in general how to identify and monitor those clogging factors, mostly in terms of trying to understand how to make decisions. And finally, we're going to talk about designing water treatment systems. So just to set the right expectation, I'm going to mostly talk today, focus on iron and biofilm management, but I will also touch a little bit in general of the other aspects that clog the irrigation system. One of the things that you want to take from the two examples that I'm going to cover a little bit more broadly is that there is not a single way that you can solve a problem, so you always want to think of how to systematically identify your problem and then how to find a solution for the specific problem. So the first thing to keep in mind is, I'm sure that if you're here, it's probably because you're not like this guy there. When you have high quality water, we tend to forget how important water is. We tend to forget that water touches every single aspect of our operations. But when we have issues with water, it becomes something that we can't forget because, again, it touches every aspect of the operation. So just to illustrate how water quality can be a very problematic and costly issue for growers, I'm going to start by showing you an example. And this is one from a grower that is in the Northeast, and it's a grower that we approached a while ago because at that time we were interested in estimating the cost and benefits of water treatment. And he had deep wells. We were trying to estimate the cost of his water. And as we were talking with the grower, one of the things he said, I have this copper system. I use it to get rid of the bacteria, but I still get these issues with iron. And he showed us, at that time he was growing poinsettias, and he showed us, we have the poinsettias under propagation, so the mist touches the leaves, and then the poinsettia grows, and then when we are transplanted, of course, we are irrigating with a dripper, so we don't get the foliage damage anymore. But we do spend a lot of time just cleaning those drip lines. So when we had that discussion, we started trying to figure out how much it cost for him to deal with that problem. At that time, he didn't think about it too much because he just thought, it's part of what we have. It's the water we have. It's the problem we're dealing with, right? So this is a greenhouse that is a 20-acre greenhouse using 21 million gallons of water a year. So one of the big greenhouses in the Northeast. So one of the things he did is he said, I don't know what the cost is, so I'm going to start tracking for a year, and then I'll make a decision on what to do. So the first thing he did is he started keeping close eye on everything that went in his business to just deal with the clogging, right? The first thing he did is he estimated how much he had to buy to replace emitters and irrigation lines. So he spent $4,449 a year. And then where he was mostly surprised is when he started tracking the labor that was involved in inspecting, cleaning, and replacing those emitters. He estimated that he was using 13,486 hours per year. That's the equivalent of 6.5 full-time employees. At that time, he was paying an hourly rate of $11 per hour. So he was spending $148,000 on labor alone just to clean, inspect, and replace those emitters. So I wish I had you here in the room to ask you, raise your hand if you have spare labor that could be doing just cleaning emitters, right? We know that labor is one of the biggest issues in our industry, so having that labor being used in this way, it's not the most efficient way because it's not only costly, but at this time we're dealing with the fact that labor is limited in our industry. And on top of that, he didn't estimate what's the cost of removing stain leaves, but he did spend a lot of time before packing or before shipping where the workers had to be removing the stain leaves to make sure that the plant looked with the quality that he wanted it to look like. When we were doing that project, one of the other things, we went around with different growers and we tried to get numbers from them in terms of how much quality their water source was costing. You can see that high quality water like municipal water, municipal water is very expensive, but it's water that it's like ready to use, very clean. The only concern you would have with municipal water is to think about whether it has too much chlorine, which in some cases it may have it if you have a susceptible crop. But then when we look at options like well water, it's relatively inexpensive, and then pond water, it's even less expensive or lower price, right? So we tend to see that, again, the higher the quality, the more expensive the water. Similar with rainwater, it's considered really pure water. In this case, the 64 cents is the grower that we just talked about. So one of the things is when we went to this grower, we look at the cost, and he said, you know, my water is about 20 cents per 1,000 gallons. When we started to look at the cost of his actual water, we have that 64 cents that I showed you earlier. But then we started adding the cost of treatment, right? Because when you're having to deal with a problem, you have to put that as part of the cost of your water. So he was already using a copper ionization system because he was trying to prevent bacterial diseases from growing up. He used fertilizer throughout his system, so we added that to the process. And then we added the labor and the cost of iron removal or dealing with iron issues, and that added the cost of his water pretty significant, right? So the take-home message from this first section is that before you decide on a treatment option, it's very important for you to know what is the cost of your water source. And by that, I really mean what's the true cost of your water source. Because if we go back to this graph, we can start thinking we don't want to pay that much for municipal water, but you see how the price really change once you start adding the cost of dealing with low quality. So even though today I'm going to start talking mostly about how to deal technically with some of the issues, you might want to consider that sometimes the best solution might be to consider an alternative water source, even though that might seem like an expensive choice up front. It's one that it's also should be part of your consideration. And you can only make those decisions if you really know the true cost of your system, right? So let's make sure we take that from today's presentation. So these are photos that I have collected from growers, operations that I have interacted with. You can see that the photos are very different. The two on the bottom right are from my research program, but all the others are from real growers. So if you look at those photos for just very quickly, I want you to think about what's the first thing that you think about when you see all these different clogging issues. And the one thing I want you to take from this is an important and the most important lesson for today. And that is that there is really no silver bullet to manage clogging. And go back to that photo and think about if you face a clogging issue and you are in a trade show and you tell someone that you have a clogging issue and the vendor immediately tells you, oh, I have this product or this technology that's going to solve your problem, you can immediately know that that person is giving you the wrong information, because you have to first understand what type of clogging you have. We have many different types of clogging, and unfortunately we don't even have the solution for all of those types. So very important to know that you need to match the problem to the technology that you're going to use to solve the problem, right? So no silver bullet. Make sure that if you're looking for options, you really try to understand, again, systematically what the problem is. So going back to the water quality, one of the issues that we have with water quality as it relates to how this water may be causing clogging is that water quality doesn't have a clear definition, because it's really something that's relative to what the end use is. In our case, when we think about irrigation, the very minimum that we expect from the quality of our water is that it gets delivered to our crop. So if the water is clogging the system, of course, we know the quality is low. And there are really no clear standards of water quality for clogging. There are a few reports that you might find if you search online that were developed in the 60s. Those reports have been reused and recycled by many researchers. I use them for some time as well. They are even posted in large organizations like the Food Ag Organization. But when we try to validate those thresholds, we realized that it's not that simple to just say, oh, I have X amount of bacteria and therefore I'm going to see some biofilm. So we don't have a clear standard, and that's part of the reason why we need to kind of try to break it down and see what's really in our own system. What we do know is that there are definitely some parameters that affect clogging in irrigation system. We know that when we think about options, we can classify them as chemical issues. Those tend to be caused by precipitation of chemicals or minerals in the solution. So you have something that's coming from the water source, it precipitates, and it forms some sort of sediment or precipitation on your pipes. The second option would be something biological, and that is when you have a type of organism that it accumulates, it's present at high concentration, it knows how to bind together to each other or to form communities that will then form something that it has a structure, a three-dimensional structure, and that clogs the system. And then, of course, we also have like more physical type of clogging, which is caused by the accumulation of sediments. And by sediments, I'm using this word lightly, something like you have too much organic matter that just accumulates in your filter, or you just have a lot of mineral particles because maybe where you're pumping your water from, you're pulling out some of the material from the bottom. So it can be things like sand, something really physical that doesn't necessarily have a reaction. So we have these three different categories. I'm going to touch, again, mostly on iron. I'm going to talk on biofilm. I'm going to touch a little bit on the physical aspects when we talk about sanitation. But the main thing with physical particles is one of the things that I hear sometimes from growers is my filter clogs pretty fast, so I have a clogging issue. And when you think about that, that just means your filter is working. And the way to solve that problem is you want to have multiple stages of filtration. So if your current filter clogs too quickly, you just want to make sure that you add another layer of filtration with a pore size that's bigger. So you have something like a stage that removes like really coarse particles and a second stage that removes the finer particles, and that will help reduce the frequency at which you have to clean your filters. But other than that, I'm not going to say very much about clogging caused to physical reasons. And this is a slide that I got from Paul Fisher. One of the things you want to do if you want to start identifying what your problem is and you really don't know where to start, you can start by doing a small test in-house, and you can throw your emitters in a bucket of water. And if you see that what comes out of the emitter or what's accumulating on the emitter, it's mostly slimy, then you can start suspecting that you have a biological clogging issue. If water alone doesn't do anything, but when you add some vinegar or just lower the pH with any acid that you might have in your operation, you can suspect that it must be a chemical issue, and then you can follow up by testing in an analytical lab. And then the final one is if the particles just wash off really easy, you can think, oh, it's probably sand or more like organic matter that simply drops out. So this is a first stage. When you really start seeing problems, you don't know where to start, this is a starting point for you to start in your operation. Now we're going to get a little bit more in depth with the chemical parameters. So when we think about chemical parameters, again, you want to think about, I have water, everything's liquid in that water, but how does the water come from what's on the left corner there to the lower right corner there into something really physical, right? When we think about those chemical parameters, the ones that tend to be an issue are iron and manganese, and I put them together because they behave very similar. Calcium and magnesium tend to be a problem as well. It's one that it's, I don't see as frequently, but it's possible that you have too much calcium. And then hydrogen sulfide is also one that may be problematic, especially if you have a specific type of organism that accelerates the flocculation in that process. I'm going to talk mostly about iron and just describe on what would the decision process would be in terms of solving an iron issue. So the first thing that I highly recommend is we start by suspecting iron is a problem. So we want to understand, okay, if I have a well, iron might be a problem. If I don't have wells, it's very unlikely that iron is a problem. So the reason is you can roughly classify water sources by the type of problems you can find. And iron issues are mostly a problem in deep wells, right? The reason for this, you can imagine if you have a very deep well and there's weathering of minerals in the surface surrounding your well, that's kind of accumulating in your well. So that's part of the reason. The other part of the reason it tends to be a problem in deep wells is that we need to understand that iron is a type of element that you can find in solution or you can find as a solid, right? The factors that promote iron to be in solution, one is that if the pH is really low, the iron it dissolves, so it's very liquid, right? You don't see suspended particles. The other reason is if the solution has very low oxygen level, again, the iron remains in solution. So again, think about if you have a deep well, there's very low oxygen concentration in that deep well. When you pump the water to irrigate, the oxygen gets into the water really quickly, and that's when the iron would precipitate, because it goes from in a condition with low oxygen that keeps the iron in solution to something that oxidizes the iron very quickly and forms into a solid. And this is one of the things that it's essential to understand when you think about management, but when you also think about diagnosing the problem. And keep that in mind. It's not that the iron there's more or less iron at different pH or at different oxygen levels. It's that the solubility is different. So you can have 10 parts per million of iron, but it may be really soluble, or it can be really like the particles that we see there, and mostly affected by pH and oxygen. So one of the interesting things about this is that I've talked to a few growers. They see their irrigation system, they see the precipitation accumulated, and it looks like rust, right? So iron is one that visually we can very easily try to grasp that the most likely cause is iron, right? It's very distinctive. But when the growers test for water quality, some of them have called me and said, you know, this looks like rust. I always thought it was iron, but there's only like 0.1 parts per million of iron in my water, okay? So part of the reason that we want to understand systematically how to work this out is that if we understand that iron is in solution when the pH is low, we can know that if the pH is too high, I'm not going to catch that when we send our water sample to get tested, right? The other thing is that when we collect the samples and how we collect them also play a role when it comes to iron. So ideally, you want to collect samples in a very airtight container. You want to make sure that it's as close as possible to the water source and that you close the container immediately after sampling. Because one of the problems that we might be facing when we're sampling for iron is that if we are collecting our sample, let's say at the hose, maybe the precipitation has been accumulated throughout the system, and it's something that I didn't capture when I collected my sample at the hose. The other problem might be that if we collect the sample close to the irrigation system, to the irrigation source, but the container was not tightly closed and there's oxygen, there might be some precipitation on the container of the sample that we collected, and it might be something that when you send the sample, the laboratory didn't notice it, wasn't looking for it, and it's not that it's a bad practice on their side, it's that it's the standard for horticultural labs to test soluble iron. So if you want to test for iron because you think you have issues with clogging, the one thing you want to do is call your lab ahead of time and tell them, I want to measure total iron. And for them, it's a very easy process to make that estimation. They just need to know that that's what you need to measure. So we're going back to this case study where we estimated the cost. So we know that the cost was really high in terms of dealing with iron. What the grower did to deal with this problem was that he did what is the standard method when you're trying to remove minerals from the water. And that is, you tend to do something as the first step where you make those minerals or those salts solid. In this case, we're calling it oxidizing. You put potassium permanganate, which reacts in the water and basically releases a lot of oxygen very quickly, and that makes the iron go into the solid form. Then you have to, once you make it solid, it's something you can remove from the solution, and then you have to have a filter. This grower chose a series of green sand filters, which are highly recommended, specialized for iron and manganese. And one of the things is that these systems tend to accumulate a lot of those solids, so it's something that ideally you want to have a system that backwashes. Otherwise, you're going to end up having to spend a lot of time just cleaning the filter. And then you can irrigate and do whatever it is that you do at the other end. So this is what this specific grower chose. I'm going to talk shortly about what other options are, but just in general, whenever you're trying to remove any type of iron from your system, one of the things you want to consider is there a way that I can easily and inexpensive make that a solid, and then you can filter it out, right? That's the first thing you want to think about, just because it's easier than to try to actually capture and remove those ions, say with something like reverse osmosis, which is a technology that also works, but it's a technology that it's much more expensive, and also a technology that requires a high level of kind of engineering type knowledge to manage. So this specific grower, he spent $200,000 in the installation. He estimated that he was saving the $152,000 that he was spending on labor and replacing emitters. He had to he was spending consumables of $17,000. So his balance after first year was $73,000. Then with the labor savings in year 2, very quickly he had already paid for this system. And again, the beauty of this example is that the grower only proceeded to do this change because he had a number that helped him make an informed decision. That the cost of labor for him was so important that he changed what he was doing, even though he had been doing it for quite some time already. And again, just remember our water earlier was like $8 per 1,000 gallons. Just by changing the cost of iron removal down here, you can see that his cost went from $8 to a little bit over $2.5. So what are other treatment options to remove iron? The system, ideally, the design, you want to think again as in terms of how you can design a system. Let's say you have a well system. You're going to create something like a retention pond. It can be something that's open, like a concrete tank, or it can be an open tank, but you want to have something where you have enough aeration to make sure that things settle. You can also follow that up with an oxidizer. Potassium permanganate is the one we talked about before, but there are other oxidizers. Chlorine is one that is inexpensive that also works really well with iron. Or you can have something as really strong as ozone, but it's not very specialized type of oxidation because it's a little bit too expensive for this option. But any oxidizer would work. Peroxides work, even though they're not as strong. Then you follow by filtration. Again, if you are not filtering after oxidizing, you're basically just creating big clumps that are going to clog your system. The other option is you can also follow by a cation exchanger. These are very common use in drinking water. A lot of people in Connecticut use them to treat their wells for drinking water. And then you can take that to storage. And here I'm just showing the best case scenario where you want to have a system that's extremely clean, and let's assume that your iron levels are very high. An alternative world would be one where you just have the retention pond and followed by filtration, or you have that containment tank and then followed by filtration, or you could also just have that cation exchanger and remove the iron. So it's not that you have to have them all. This is kind of the ideal situation. And then the other thing is that there is also the option where you can keep the iron in solution. You can add an acid or chelating agents. that prevent the iron from becoming a precipitate, I wrote that note just because that's what you're going to find in the literature. I don't recommend that a grower would do that, mainly because the conversion from iron to solid, if the pH changes, it's very quickly. So having it as in solution by manipulating with acid tends to be kind of not very stable. So that's one of the considerations, that I think the other systems tend to be more effective because you're actually removing the iron from the water. So this is a photo. It's not specific to iron, but it's a system where they were trying to remove other ions. And you can see that it's very similar to what I was describing. They had first their catchment pond where they were having these multiple aeration systems. Some of them are off, but they're like in the middle of the retainment tank there. Then they put the water in this concrete tank, and they added whatever was going to help with flocculation or oxidation. And you can see that things started to settle at the bottom of the tank. And then they had what was an ion exchanger, and then some filtration to follow with that. So the system can be very simple. It looks a little bit more complicated in the cartoons, but even small farmers can do something along these lines. So just to summarize the iron aspect, the one thing you want to understand is you want to understand the problem, because something as simple as remembering low pH and oxygen are going to keep the iron in solution and vice versa is one thing that once you understand, you can start making decisions about, oh, this is why it doesn't pick up in my water test, or this is why we see it here and not here. So those are kind of things you want to understand to solve the problem, and also to be informed when someone's trying to give you a treatment option. The other thing you want to know, and it goes very connected to the previous one, is that if you understand the problem and you understand what you need to test for, you are going to make the right test. In the case of iron, you want to test for total iron, and it would be similar with manganese. You want to make sure that you ask the lab to measure for total levels. And then finally, in general, with iron, you want to think about forming solids or oxidizing, and then removing through a filtration system. Again, there are other options that we touched briefly on, but this tends to be one that growers use and are happy in terms of it removes the iron well enough, but it also is simple to use. And the other, just to go back to testing for total iron, that also helps you determine what rate of, say, potassium permanganate, because it's a ratio of 1 to 1. So if you don't have that right number, you might be adding too much, too little. So just make sure that that's tied to, that the treatment is tied to your test. So now we're going to go with biological clogging agents. When we think about this, the two that always come to mind is having too much bacteria, or a kind of bacteria that, again, binds together, grows, and forms this structure like that emitter there, and that's a real emitter from a grower in Florida. And we tend to see that in greenhouses and nurseries, we tend to see this combination of bacteria and algae. Most of the time when we see these like greenish, it's like a type of algae, like blue-green algae, that combines and takes advantage of how the bacteria is growing up. So we are calling this biofilm, and we know that biofilm is pretty ubiquitous in wherever we have water movement. And the one thing, like we talked before, something like iron tends to be an issue more when you have well water. But when we think about biofilm, all water sources can result in biofilm formation. So even though you may start with water that's extremely clean, the fact that the water moves through a system results in a biofilm accumulation. And I'm going to show you some of that in the next one. But I really love this photo from Peter Conjoyan, because you can see that you start with a very clean system, but if you're just letting water flow, and to be honest, I don't know what water source he was using, but to just let water flow through, and it can be like we do experiments, and we've tried municipal water, we've tried pond water. We like pond water because it has a lot of microorganisms, but we also see that just using tap water from our system, we still get biofilm buildup. So regardless of the source, biofilm will accumulate. And then the one that you see, the algae biofilm complex, is one that it's really problematic for industry, especially for greenhouses that continuously inject fertilizers in the solution. Even those pipes that we think, some of the pipes prevent light transmission. Some of them are dark and are supposed to be like UV, have a UV protection. You still see algae and biofilm complex form in there. Don't ask me why. I think there must be something, like maybe there's a type of algae that doesn't need as much light, or it could be that the materials are more porous than we think they are. But definitely we see those across different production systems. There are different ways in which these problems are monitored. So one of the things that the way we've been doing it traditionally is that we just count how much bacteria is in the system. We don't have a clear threshold of what that level is. Again, like I mentioned earlier, we used to have a threshold that we used, but we haven't been able to validate that threshold, so we think it's more related to the type of bacteria that's there. But in general, just knowing the amount of bacteria before and after treatment can tell you a lot. So you can use different types of media. The one you see there at the left is like the traditional agar. The one in the middle is something that's called dehydrated media. So it's also agar, but it's just dehydrated. And then similarly, you can do the same with algae, where you either grow it in a plate or grow it in a liquid media and then estimate how much is in there. And that basically tells you, is there a lot, is there a little, but it doesn't tell you too much about the type of bacteria that's there, or whether, even if it's pathogenic, if that's one of your concerns. But it's a very good indicator, especially if you're treating water. Let's say you're injecting chlorine, you should at least see a difference between the before and after, right? So very useful tool for that sense. So like I was saying before, one of the things with biological issues is that even if you start with very clean water, and you can see in this table, the top row, it's the average of multiple greenhouses that were sampled. And the water source has very low amount of bacteria to begin with. When you measure, for example, the water, for example, in ponds, those numbers tend to be higher than that, but still they tend to be lower when you compare them to furthest outlet. What happens when you have water sitting in a tank, or what happens when you have an ebb and flow system. Just the simple fact that the water goes into the plant and comes back, it just comes like really rich of bacteria. And then pond water, which in this case it was whatever was the catchment ponds, you can see that the numbers are even greater, because I assume they just get in there and start accumulating because there's enough organic matter to feed the bacteria. So again, you regardless of a water source, as the water moves through the system, you expect that biofilm will start accumulating. One of the things that we've been trying to do in our lab is just trying to understand what is it that we do that we can change easily and avoid having too much biofilm, because we don't think we can get rid of it, but we can think we should be able to control it to a certain degree. And what you're seeing here, we were measuring, like we said, colony-forming units. So it's the number of individual bacteria that was recovered. And we also measure the biomass of the biofilm. So if you look at those two blue lines, what you're seeing is the amount of bacteria or biomass that accumulated on PVC pipes. And then what you see in the orange lines is what accumulated on polyethylene pipes. And this is something that we conducted in our greenhouse, similar to what propagation greenhouses or propagation houses would do. And what we've seen consistently is that PVC tends to be a material where bacteria accumulates faster. I forgot to add a photo, I think, where we showed how the bacteria changes the surfaces of PVC, and we just think that the PVC tends to be a material that it's like a better material for the bacteria to grow, and it's easier for the bacteria to degrade that materials. So PVC tends to degrade faster. PVC also tends to harbor more bacteria, so basically it feeds the bacteria a little bit better. So we've seen this consistently. We think it's a small change, but I don't think it's that significant yet to think of it's going to prevent biofilm. Like I said, biofilm will grow regardless. And this is a little bit of how the photos would look. You can see that we also try different irrigation rates. And the one where you see here 30 minutes every 30 seconds on every 9.5 minutes, you can see that the biofilm started to form that little structure. And this is just in 4 weeks. So definitely a small change that could make a mild difference there. The other thing that we've learned is we're trying to understand how clean do we need to have our pipes. And one of the things we looked at is, okay, if I start with a system that's extremely clean, or if I start with a system that has some biofilm to begin with, what happens to pathogens that go into the system? And the reason we wanted to know this is because there's all this concept that if you've heard about gut microbiome, right? Is there such thing as a gut in the pipe kind of concept? So we wanted to see if you look at here, the ones that said plus biofilm, basically here we added pythium and here we didn't add pythium. And when we had biofilm, we had lower disease incidence, so meaning fewer plants had pythium root rot. And then when we compare that to root infection, the root infection also went down. We don't know why or how this works, but I think the lesson that we're taking from this is we need to keep a clean system. We want to make sure that if we have a biofilm issue where it's really clogging the system, then we should start thinking about treating. But if we don't have a system that's being clogged, I think it's just enough to make sure that you flush your system once in a while, but there's no need to treat if you don't really have a problem, because the more we know about how, again, the concept of gut microbiome is the one that's more popular in the literature, it seems like there might be something like that going on in the pipes as well. But assuming you have problems, you can switch to that now. The general biofilm control methods would be, first you want to make sure that you can shut the line once in a while, right? You want to remove your small emitters and then blow them out and make sure that you can flush the system so whatever particles are accumulated in there can get out. When you have no plants between seasons, you can also do a sanitizing shock where you inject a lot of sanitizer at a higher concentration. If possible, you can let it sit overnight, because the longer the contact time, the better those sanitizers work. And just make sure you flush it really well with clear water afterwards to make sure you don't have a residual concentration. And then the third step would be, this is if you're having issues, you want to make sure that you think about how can you minimize the accumulation of biofilm. And that's going to be very similar to what we talked before, but we're just thinking about it in the opposite direction. In this case, we want to have a filtration system first and then followed by a sanitizing agent at a low concentration. And the concentration is really critical here, because you don't want to start, you want to make sure that you're not using the shock concentration at a continuous use because of crop sensitivity. So now we're going to talk about water treatment design a little bit more in detail. Again, the first step when we think about getting rid of biofilm is you want to get rid of whatever is going to help the bacteria accumulate. And the first thing is to get rid of any type of organic matter that may feed the bacteria or that may harbor bacteria. So start with a filtration system. And the reason for that is, one, you're trying to get rid of the inoculum, but secondly, think about if you're injecting a sanitizer, you don't want that sanitizer to react with the organic matter that is in the water. Instead, you want it to make sure that it kills the bacteria or the algae that's going to cause a problem, right? So, for example, if you don't filter, you're going to have that reactant. And an example here is like, let's say you're injecting 5 parts per million of chlorine into your water, but the water is really dirty, and then the water reacts with that chlorine, and basically it only leaves 2 parts per million for your system to go, for the system to get clean. So you're losing some of that sanitizing power by trying to cover that demand. So instead of that, you can just filter the organic matter first and make sure that the product you're injecting is actually working throughout the irrigation system. This is especially important in biofilm control, because when you think about biofilm control, you want something that goes through the system, right? Unlike when we think about pathogens, if you think about pathogens, you're trying to kill them in a single place, and that might be enough for pathogens. But for biofilm and algae control, again, just think about how it moves throughout the irrigation system and how it accumulates. So here are just some few examples. You can start with something really coarse. You always want to start with something coarse. You can see how much organic matter was in that specific filter system. You can go then further with something that has a smaller pore size, something like a vibrating screen, micro screen, drum filtration, or an inline screen, whatever system works for you. But the important thing is you want to go from something coarse to slightly finer. And then if you have like real issues with algae especially, you want to consider using something like a sand filter that has more of a small pore size, and it also helps remove some of the organic matter as well. And then paper filter is one that you can customize to the pore size. It's one that tends to be a little bit more expensive, so you always want to leave that kind of at the end with a really fine pore size. So we have removed the organic matter, anything that will either directly clog the system or anything that will accumulate bacteria. And then the step 2 here would be to sanitize. Basically, you want to see if you can reduce the amount of bacteria that will accumulate or the amount of algae. You want to think of chemical sanitizers for this specific application, again, because you want something that has a residual effect. And again, try to visualize how that sanitizer should be moving through the irrigation system to make sure that it cleans the pipes. One of the cautions is whenever you have something with residual activity, which is a good thing, you want to keep in mind that your rates need to be something compatible with your crop, because you want to avoid phytotoxicity and you want to avoid having too much leachate of those chemicals into the environment. So this is just a photo of chlorine injury in pansies. You can see you can hurt them really badly if you overdose. And then this is just another photo of using too much chlorine as well. And you can see how you can measure. If you do the wrong measurement, a grower would rarely use doses like high, like 8 or 6 or 16 or 32 parts per million. But if you don't filter, you might think that you need to put more chlorine to overcome that demand. And if the demand changes for whatever reason, you might end up with a lot of phytotoxicity. So very important to try to keep things clean and on the low end, and always keep in mind that before you inject anything to your irrigation system, there might be a risk of phytotoxicity, so start small and with the lowest dose possible. I'm going to talk a little bit specific about algae here, just because this is another point that's really good to make in terms of phytotoxicity. This is a project that was conducted by Paul Fisher in the University of Florida. And at that time, what he was trying to evaluate is, are there any sanitizers that we can use in propagation that would help remove or prevent the accumulation of algae on the surface of growing media? And one of the things that he observed is that what they were doing is that they were injecting calcium nitrate at 50 parts per million nitrogen and apply it continuously for 2 weeks. And then they measure how much algae was left. So what they observe is, if you have no fertilizer, like on the first one here, you can see some algae grows there, but it's not very dramatically. As long as you add fertilizer, you will have algae, and that's very similar to what we see in the pipes. And then the third thing is he saw that copper sulfate would reduce the algae pressure. We have products like Xylitol or X3. They're very similar products, but you can see X3 wasn't as good as Xylitol. Xylitol did reduce the algae. And then we have this last one, chlorine dioxide, wasn't that effective at removing the algae. The interesting thing here is that if you see these ones that have that were good at suppressing algae, were also the ones where the plants, even though they didn't have visual injury, you can see that the biomass of the plant was much smaller. So there is this dilemma that we're trying to figure out in terms of how to control algae, and that is, how can we prevent algae from accumulating in the pipe without killing the plants or without losing growth? And that's a very hard task that we don't have a good solution for, but that we're working on and trying to understand a little bit better. So again, keep that in mind as you're choosing a sanitizer, because you might not have the side-to-side comparison in your operation to decide to see if there's a negative effect. So that's another thing that you want to take from this. If you're injecting something new, try to see if there's a way where you can have kind of a control where, okay, this one's not receiving that treatment. Is it growing at the same rate, even though the rest of the conditions are all the same? So important to make those tests in-house as well. And we are working with the Horticulture Research Institute in trying to figure this problem. So we're looking for growers who have algae issues and would like to be part of our sampling. So if you are one of those, please contact me and we'll follow up with you. And so getting here to the end, one of the things is you might be asking yourself is, okay, you've said how to design it, but I really want to know which technology I should be using to get rid of the biofilm in my system. And I really can't tell you which one would work. We think that there are products that work really well when they are in gas form. So products like chlorine dioxide tend to work well if they are like an immediate shock. But again, when you think about biofilm and how things accumulate throughout the irrigation system, the longer the contact time, the longer the residual, the better it will be on cleaning throughout the system. So when we compare that to technologies like UV, heat, or filtration, those just treat the water at a point system, right? So they treat it there, and then once the water leaves the treatment system, you don't see a lot of effect on you, or you don't see any effect, right? Once the water leaves that system, it's not being treated. So again, things like chlorine dioxide, chlorine, they have a little bit more of residual activity compared to something like UV, but there are others that are really slow and they tend to do a relatively good job. Things like chloramines or parasitic acid, so that's similar to the Xylitol X3 products. So you want to play a little bit with those, and the reason we don't have a good answer on which one's the best for you, it's because a lot of these products will have to be matched to the actual type of bacteria that it's in your system, and that's where we don't have a lot of information yet. But you want to see that you want to get one of those that have some residual effect. Definitely something like UV would not be a good option for treating biofilm. And again, just think about treatment design. You want to consider what your water source and what the likelihood of problems are. You want to have a multiple stage filtration. You want to inject a chemical sanitizer for biofilm, and think about how if you can keep it for longer, you're more likely to have an extended contact time and therefore reduce the inoculum. And then you can filter again just to make sure that you have a very consistent before it goes through to the plant. So in summary for the biological and clogging issues, in some additional comments, is just think that biofilm will accumulate regardless of your water source. So think about if you have an issue that it's like severe issue, you want to keep in mind that you will have to shock eventually, and hopefully you have some time in your season, between seasons, where you can do it, because regardless of water source, and especially if you're using liquid fertilizers, you're going to see the biofilm accumulate and you're going to see a biofilm algae complex. We are seeing that biofilm tends to accumulate more in PVC than polyethylene. So for those in propagation houses, it seems like polyethylene would be a better choice. And then just overall think about water treatment and think about design. It's never going to be about just installing a piece of equipment or just injecting one product. As you can see, you either need a filtration system that pairs with the system you're doing. The type of filter might play a little bit of a role, but also flow rate and all of those other aspects are things to be in consideration. And one of the things I haven't talked much about is that tanks give you a lot of power when it comes to what type of treatment design you want to do. Every time you have a storage tank, you can control the flow rate The slower the flow rate, the more contact time you can have. The smaller you can have a treatment system. You don't need to have like a massive treatment system that goes at a high speed or a high flow rate. So think about that as well as you're thinking about water treatment design. The other thing is, again, going back to what we talked earlier, when you're thinking about the cost of water, one of the things that we've learned is that when you compare the cost of water to the cost of treatment, it tends to be the treatments there are the little bars in yellow. And what you can see is that the treatment tends to be relatively inexpensive compared to the cost of water. And if you are using water-soluble fertilizers, definitely if you can capture and reuse that water, you're saving money. And then treatment tends to be not as expensive. I'll just end by saying we have developed something called WaterQual. If you go to cleanwater3.org with Jim Owen, he's also part of this group. We developed a tool that helps you make interpretations about water quality. As I was preparing this presentation, I realized there's very little in terms of precipitation and how to deal with those problems, but it's something that we're going to add. But there's a lot that you can find in terms of nutrition, and there's a little bit on the biofilm aspect as well. So just final take-home messages here. Make sure you identify the cause of the clogging. You can start by doing something really rough in-house, but then follow up by conducting the correct water quality test. Understand the problem. So it's not just about knowing what the problem is, but understanding the dynamics of, okay, I have algae, so it's a fertilizer issue. Maybe I'm never going to get rid of it, so I should be trying to get rid of those spores by filtering, and also having something with residual effect, or understanding the problem of how pH plays a role on iron. So those are I like those examples because it gives you a lot of information of things that should be considered before you even decide what to do. The other thing is you want to estimate the cost of a water source, and by that I mean the true cost of your water source, and that means what's the cost of that problem and what really will help you choose an alternative water source or choose an alternative treatment option. Again, choosing an alternative water source should be part of the things you want to consider if that's an option for you. But you can only make that really informed if you have those numbers. So take the time to estimate those costs. And then finally, design a water treatment that matches the problem. Make sure they match. Make sure that if you hear someone telling you, my technology is going to solve your problems, it might be true, but make sure you understand all of the items listed there before you actually go into making that decision.